the plan, of course, is to just kind of continue class as we have. We just have to do it online, but it'll be pretty much like regular class. Maybe it'll even be a little bit better, because if you've got something on GeoGebra that you want to share with the class, then you can just share your content and we can all see it, instead of me just looking at your laptop if you're in the same room as me. So maybe it'll be even better for us. It's easy to share content, by the way. I think that should be available for everyone. You can just share a screen or share whatever application you're using, and it works pretty well. If you happen to not have audio, or something happens with your computer and it's not working, you can always dial in for audio. There's an option for that, so you can use your telephone for audio. So does anyone have any questions about anything before we get started? Okay, well, I think we're just going to jump into it then. So Roger and Mario, are you able to hear us okay?
Nope. Yeah, I can hear you.
Okay.
Yes, sir, I can hear you.
Okay. I just have myself muted because my house is loud sometimes.
Yeah, that's fine. Just checking.
Yeah, me too. I have kids.
Yeah, well, I've got mine, and they're going to go to bed at some point, so I probably hear them. Okay, so I'm going to share my screen and just start the lecture. So can everyone see my slide there?
Yeah, I can see it. Looks good.
Okay.
Yes, sir.
All right.
Yeah, I can see it.
Okay, so we'd kind of started this, I think, before the break and the apocalypse and everything. That we'll back up to where we were, I think, right at the beginning. And we'll spend a bit of time trying to construct some things together in class today, because I think, we're getting into the true topic for the course, and I have some techniques for plotting these in 3D, but I think it'd be good to have some practice with it. So you all be ready to follow along with GeoGebra, and we'll try to construct some things together. Okay, so to start back with the beginning then. Polytope is a general term of the sequence, with the terms point, segment, polygon, polyhedron, and so on. And we're going to be using analogies to draw a lot of conclusions about polytopes. So, we're going to think about analogies like, well, as a polygon is to a polyhedron, so a polyhedron is to the four-dimensional polytope. And we're going to use everything we know about polyhedra, which is a huge amount at this point, and try to make educated guesses about what would be true for polytopes. Okay, and so at the beginning of this chapter, Coxer talks about how there's three ways of approaching four-dimensional geometry, which is axiomatic, algebraic, and intuitive. And so there's this quote by Poincaré that we mentioned last time: "A man who devoted his life to it could perhaps succeed in picturing to himself the fourth dimension." And Coxeter says only one or two people have ever attained the ability to visualize hypersolids as simply and naturally as we ordinary mortals visualize solids. But a certain facility in that direction may be acquired by contemplating the analogy between 1 and 2 dimensions, then 2 and 3, and so by a kind of extrapolation, 3 and 4. So that's our goal today, is to just sort of, extend the analogy, to use the third dimension to imagine what the fourth dimension is like. Okay, and so, Schlafly, whose name we've encountered a few times, first published a work on polytopes in the 1850s. No one really noticed it at the time. I think it was a couple of books, 2 volumes or something, but no one really noticed it at the time. But then all of a sudden, a few decades later, everyone started studying it at once, and all these people independently rediscovered them. It also made its way into the popular media. So there's this famous book, Flatland, that probably all of you have read. It was written by a schoolmaster, Edwin A. Abbott, and it's not really clear where Abbott got the idea to write about the fourth dimension from. There were some other popular authors at the time who were thinking about it, and so either Abbott influenced them or they influenced him. No one's really sure who was talking to whom. But at any rate, in 1884, this strange little novel came out, and it uses dimensional analogy in a very powerful way to help the reader imagine what the fourth dimension is like. So we've got these 2 analogies right here, where he talks about an arithmetic and a geometric sequence. So, just to draw a picture, and I probably have drawn pictures like this before. Let me sketch this out. Yeah, so he says, see, in one dimension, did not a moving point produce a line with 2 terminal points? So, you start with the points. And it moves. And, you get, so I'll start with a point here. So it moves and you get this line segment with 2 terminal points. And then he says, in 2 dimensions, did not a moving line produce a square with 4 terminal points? So, this point moves this way. Imagine this line segment moving that way. And you get a square with what he calls 4 terminal points, or vertices, we would call them. And then, you imagine the square moving that direction, maybe, in the 3rd dimension. And we get the cube with 8 vertices, 8 terminal points. Okay, and so, we've got, I'm sorry. So, we've got 1 point and then 2, 4, 8. And then, so, this character in this book, he's like, well, why would you stop there? What would correspond to 16? You've got this arithmetic sequence. It's a geometric sequence, 1, 2, 4, 8. Each time we're multiplying by 2. So what corresponds to 16? Well, by analogy, what we'd have to do is take this cube and move it in a perpendicular direction. The only problem is in 3 dimensions, we've run out of perpendicular directions. So you'd have to move it in some direction that we haven't defined yet. Okay, and then so again, he talks about how in a line there's 2 bounding points. In a square there are 4 bounding lines. In a cube there are 6 bounding squares. So in the line we have 2 bounding points. In the square, you have 4 bounding lines. In the cube, you have 6 square faces. And then, yes, 2, 4, 6. Well, what about 8? So, you know, in the next step in the sequence, we would expect there to be, 16 vertices. And we'd expect there to be 8 bounding cubes. So we'd have to imagine this thing that is made up out of cubes. It's made up out of 8 cubes and it pasted together along their faces, so to speak. Just like a cube is made up out of 6 squares pasted together along their edges. Okay, and so he's, the character is, using this geometric sequence and an arithmetic sequence to make us think about what would be the next geometric object in that sequence. Okay, and Coxeter has a few words of caution about the intuitive approach. Probably he included this because, especially back then, a lot of people were getting weird ideas about the 4th dimension. Spiritualism was very popular back then. So that was the idea that you could communicate with the dead through things like Ouija boards and seances. So that was really popular at the time this book would have been written, and a lot of those people appealed to 4-dimensional geometry to explain some of what they were trying to do. And so, he says that there's nothing mystical about the 4th dimension. There's no evidence that a 4th dimension of space exists in any physical or metaphysical sense. We merely choose to enlarge the scope of Euclidean geometry. And that's not exactly true anymore. At any rate, it's not true that there's evidence that a 4th dimension of space exists now, but there are theoretical physicists and mathematicians that are trying to use the idea of additional spatial dimensions to make some of the laws of physics work out. In particular, they're trying to figure out some way of making general relativity reconciled with quantum mechanics. And most of the attempted solutions involve appealing to higher dimensions. Maybe it's sort of like, here's an example. Let me sketch a little bit again. So, a curve, if you just take a curve in space or in the plane, that's a 1-dimensional object. Okay, so, and if you lived in this curve, you'd have a 1-dimensional spatial universe. And that's something that Flatland thinks about a little bit. But suppose instead of just a string, basically, it's a really skinny tube. And if it's skinny enough, then you wouldn't notice that it's not actually just a curve. It's actually a two-dimensional surface where you can move two directions. You can move along or you can move around. But because the around direction is so tightly curled up, physically maybe you wouldn't notice that. So the idea is that we have three spatial dimensions that are big, that that's what we experience in daily life. But maybe there's additional directions that are just curled up so tightly they're not physically detectable. But maybe there are weird quantum things going on in those directions that would help explain some of the laws of quantum mechanics in a better way. And I know a little bit about that because I spent 7 years of my life working on a PhD where we focused on that. And I don't know if that's ever going to pan out to anything, honestly, but it's an idea that people have right now. Okay, and then Coxeter also says that guessing is fine, but you have to verify things axiomatically or algebraically. So you really have to make sure of all this. And then he also says little, if anything, is gained by representing the fourth Euclidean dimension as time. So there are some examples here of falling into these various errors. One is this person, Charles Howard Hinton, who wrote about the fourth dimensional quite a bit and helped to popularize it. But he kind of began this idea that you could explain spiritual phenomena, stuff like that, through the fourth dimension. And his book, A New Era of Thought, kind of gets into some of that. And so, as Coxeter says, many advocates of the intuitive method fall into a far more insidious error. They assume that because the fourth dimension is perpendicular to every direction known through our senses, there must be something mystical about it. And so Hinton I've cited as kind of an example of that. And Coxeter, I don't think he knew Hinton, but he knew people who knew Hinton, so probably knew quite a bit about him as a person. And he's probably thinking of Hinton more than anyone else when he was making this warning. And so he also talks about how it's not really helpful to think of this fourth dimension as time. And that's because we're thinking about four Euclidean spatial dimensions. In modern physics, you do think about time as a dimension, and that has meaning, but you don't use the Euclidean distance function in that. The time direction is negative, basically, instead of positive. And so for what we're doing, it's not helpful to think of time as the fourth dimension. There's this famous book that came out in 1898, The Time Machine, which is a very, it's an early work of science fiction, and it's a very good book. It's one of my favorites. But there's this chapter at the beginning that goes into some of the mathematics, and it's quite horrible because it's really just kind of nonsensical. But this is using the idea of the fourth spatial dimension as being time, basically. And it actually cites some of the research that was done at that time in four spatial dimensions, but it mixes it up with time, and so sort of makes this nonsensical discussion. There is some value in some of the ideas of which we'll return to in the next couple of chapters. And then there's a science fiction novel that I read when I was a kid. When I was in high school, or in junior high, really, this was pretty popular to assign for reading, 6th or 7th grade or so. It was one of my favorite books when I was a kid, and it actually helped get me into mathematics. But the math is pretty terrible in this also. And so it talks about how, well, you know, you would call the fourth dimension time, and then the fifth dimension you'd square the fourth. Then the fifth dimension is a tesseract, and you can add that to the other 4 dimensions, and you can travel through space without having to go the long way around. Which is, I mean, it doesn't really make any sense. And it doesn't have to because it's a children's novel. But, you know, throwing around some of the terms that we're going to encounter, such as tesseract, which is a 4-dimensional version of a cube. Okay, so now let's really get into it. So the space of no dimensions, the only figure is a point, which we'll call pi naught. That's a capital pi. So that's like point land in flatland. Space of 1 dimension, we can have any number of points, and 2 points bound a line segment, which we'll call pi 1. And that's the 1-dimensional version of a polygon. Okay, a polygon we'll call pi 2, and a polyhedron we'll call pi 3. So you think of a point as a 0-dimensional polygon or polytope. A line segment is a 1-dimensional polytope. A polygon is a 2-dimensional polytope. A polyhedron is a 3-dimensional polytope. Okay, so by joining a pi naught to another point, you get the line segment pi 1. By joining a pi 1 to a third point, you get a triangle, which is a pi 2. By joining the triangle to a fourth point, you get a pi 3, the tetrahedron. So in my slide here, you know, here's the pi naught. You join it to another point, you get pi 1. You join that segment to a third point, you get the pi 2 triangle. And you join the triangle to another point, and you get pi 3, a tetrahedron. So the idea would be to join the tetrahedron to a fifth point, and that would give us the pentatope, which is the simplest pi 4. So I have that drawn here just kind of schematically. The only way for us to imagine it is to project it into 3 dimensions. Okay, but you know, I've got the 5 points here. They're all connected by line segments. Each point is connected to every other point by a line segment. Every 3 points are the vertices of a face, and so you know, we can think of this as just basically a flattening of the pentatope. It consists of 5 different tetrahedral cells. You know, you've got the outside cell that contains all the others, and then you've got this kind of flat cell on the bottom with the 3 base vertices and then this vertex in the middle. And then between those, you've got 3 around this vertex in the middle that are inside of the big tetrahedron. So there's 5 tetrahedra in all here. Okay, but they've been sort of pushed on top of each other because we have to represent this in the 3rd or the 2nd dimension. So it's kind of like, you know, if you draw a picture of a tetrahedron on paper, then you're flattening it to the paper, but your eye kind of reads it as being 3-dimensional. And let me just draw a simple picture of that. So, you know, I can, if I draw a picture like this, okay, so far that looks like a triangle, but if I put a point here, then all of a sudden you start seeing it as a picture of a three-dimensional object. Okay, but it's two-dimensional. It's 1, 2, 3, 4, 5, 6 line segments on a piece of paper. Okay, there are 4 triangles here. You've got the outside triangle, this triangle, this triangle, and this triangle. So there's 4 triangles, 6 segments, 4 vertices. It's a two-dimensional object. And you can think of it as it's just a drawing or maybe a shadow of this three-dimensional object. But if you imagine the tetrahedron rotating around, these line segments could cross each other. Okay, so maybe you could imagine this one in the front. I'll make it darker so your eye reads it easily or more easily. Yeah, that's the one that's kind of in front, and then this one goes across behind. So it's a picture of this three-dimensional object, but what we're literally seeing is it's two-dimensional. Again, you've got 4 vertices, 6 edges, and 4 triangles in there. And so, you've got all these different ways of representing this three-dimensional object in 2 dimensions. So similarly, we can represent the 4-dimensional pentatope in 3 dimensions. In the slide, it's actually represented in 2 dimensions because it's just a picture. But you can imagine building something like that out of wire. And yeah, that's something I've actually done before for some of these polytopes. And if you do that, this structure made out of wire would be a 3-dimensional, quote unquote, picture of a 4-dimensional object. So you could think of maybe like the outside tetrahedron as the one that was originally in our space. In this point in the center, it was up in some direction we can't imagine in 4-dimensional space. But then someone pushed it down into 3-dimensional space. Okay, so you just continue in this fashion. You take line segment at a 3rd point and you get a triangle. You take a triangle at a 4th point and you get a tetrahedron. At a 5th point and you get what we call a 4-dimensional simplex. And then you add another point and you get a 5-dimensional simplex and a 6-dimensional simplex, and so on and so forth. So these are just schematic drawings, so we can see how all the vertices are connected. But basically, you're taking n+1 vertices and connecting each vertex to each of the n other vertices. So in this picture down here, we have, I said it's a 6-dimensional simplex, but that's not correct. It's a 5-dimensional simplex. So that's a 5-dimensional simplex. And I've highlighted in red one of the tetrahedral cells that make it up. And that tetrahedron contains 4 different triangles, which I've shaded in different ways. Okay, and in this figure, I can pick any 4 vertices and they will form a tetrahedron. So again, this is an object that is 5-dimensional. It would live in 5-dimensional space. Okay, so this is going to come in handy. So maybe this would be a good point to pause for a moment and try to construct something like this on GeoGebra. Check everybody now. Okay, so I'm going to do this in 2 dimensions. And what I'm going to do is not very deep. I'm just going to try to make this kind of figure using a slider. And I'll have to kind of remind myself how to do it as we go. But let's begin with the point 1, 0. And we'll make an n simplex. N goes from 3 to 30, I suppose. I'm going to begin by making the vertices. So I'm going to do sequence. I'm going to rotate that point A through the angle K times 2 pi over N, where K goes from 0 to N minus 1.
Hey, Dr. Tees, can you show the input bar on how you did that list?
Yes. Can you see that?
Sequence, rotate, A, I, K, I, okay, I see, okay, K2, pi, that 2 pi over N.
Yes.
And close parentheses such that K goes from 0 to N minus 1. Okay. There it is. I got it.
Okay.
All right.
Okay, so next, I want to make the edges, and I want to do it in a kind of a careful way. You know, I want each vertex to be connected to every other vertex. That's what makes the simplex. But I don't want to repeat any edges. So I want the exact number of edges that I need. So for instance, like this first vertex, okay, that's going to get connected to all of the other vertices, and there's going to be n minus 1 of those. And then this guy, the second vertex, I'm going to connect it to all of them except the one that I started with. So we're going to be connecting it to n minus 2 of the vertices. And then the third vertex, I'm going to connect to n minus 3 of the vertices. So I skip the first 2, and so on. So I'm going to have to do a sequence of sequences. There's going to be a sequence of line segments for each of the vertices. So if I just start with one vertex, like from the first sorry, if I just start with one sequence from the first vertex, you'd have sequence, let's see, segment from, just for the time being, let me just put an A, since that was the original point, to the element of the list L1, comma, K, where K goes from it go from 2 to n minus 1, I think. No, 2 to n. There we go. So this is not the final thing that I really want, but let me just go ahead and create that thing. I think I repeated something here. Okay, so what's that doing? It's creating the segment from the initial point A to the kth element of our list, where K goes from 2 to n. So I start with the segment from A to point 2, and then point 3, and then point 4, and so on up to point n. Okay, but I want to do this for each I want to do this for each point, not just A, but each point. But I have to remember that for each successive point, I'm going to start. I'm not going to keep starting at 2. It's going to increase every time I proceed to the next point. So I'm going to delete this thing in a minute, but let me just leave it there in case we want to refer to it. Let me kind of move this up so it's easier to see if you need to see it. All right. So instead of putting A there, I'm going to do elements L1, comma M. And I'm going to make a sequence of those where I want the M to go from 1 to n minus 1, I think. But I want K to go from m plus 1 to n. Okay, so let me pull that up again so you can see it more clearly. Okay, so it's a sequence of sequences. Okay, each individual sequence is a sequence of segments. Okay, so I'm taking the element, the segment from the vertex M to the vertex K. Okay, the M goes from 1 to n minus 1. So M ranges through all of these vertices except the last one. So it goes up to the second to last vertex. Okay, that's how the M ranges. And then for each M, the K goes from m plus 1 up to n. So for example, if M is 3, then K would go 4, 5, 6, 7, and so on up to n itself. So I would be drawing, like from this third vertex, I would draw this segment and so on up to this segment. And so for each successive vertex, the number of segments that I draw goes down by 1. And we'll make sure this works as I slide n around. And that seems to work. Yeah, so there's our 2 simplex, the triangle. There's the tetrahedron. That's the 5 simplex, the pentatope, and so on and so forth. So any questions on how we did this? It's like when n equals 15, that's a 14-dimensional simplex. But we're projecting it to 2 dimensions. And we're not really being careful about distances. So this is just sort of a schematic diagram of it. Okay, so in the simplex of dimension n, there are n plus 1 vertices. There are n plus 1 choose 2 edges, n plus 1 choose 3 triangles, n plus 1 choose 4 tetrahedra, and so on. So there are nk equals n plus 1 choose k plus 1 elements of dimension k. So for example, let me do 1 or 2 of these on paper. Simplex of 3 dimensions. Okay, so that would be the tetrahedron. Let me remind myself of the formula. So there are going to be four vertices. With 3 plus 1 equals 4. The number of edges is n plus 1 choose 2. So it's 4 choose 2. So that's 4 times 3 over 2 times 1, which is 6. The number of faces is 4 choose 3. 4 times 3 times 2 over 3 times 2 times 1, which is 4. And then the number of tetrahedra, the number of cells. I guess I'll count that. Of course, that's just going to be 4 choose 4. 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1. There's one of those, obviously. Okay, so let's talk about the 4-dimensional simplex. Okay, let me sketch a picture of it here. Coxeter typically draws it as a pentagram in a pentagon. And that's what our GeoGebra construction does. Okay, so if I look on here, let me just show it in one tetrahedron. That thing there on the bottom, if I let me draw it to the side, smaller. Imagine it. Let me do it kind of like that so you can see how that's supposed to be a tetrahedron. Oops. Okay, but so let's count using the formulas. So the vertices, it's 4 plus 1, which is 5. The number of edges is 4 choose 2, which is 5 choose 2. Five times 4 over 2 times 1, which is 10. And there are 10 edges here. The number of faces, this is the number of triangles that you'd be able to count in here. Well, I mean, it's kind of easy to see where these formulas come from. If I pick any 3 vertices here, that's going to make a triangle because every vertex is connected to every other vertex. So it's the same as asking, well, if I have a club with 5 members and I want to choose 3 members to form a committee, how many different committees could I form? Well, that's 5 times 4 times 3 over 3 times 2 times 1. Which is, let's see here, 60 divided by 6 is 10. Okay, the number of tetrahedra. Five choose 4. 5 times 4 times 3 times 2 over 4 times 3 times 2 times 1. It's 5. There's 5 tetrahedra in here. And then, there's 1 5 simplex. We won't write this one all out, but it's 5 choose 5. And you just get 1 for that, of course. Because, and I should have said not 5 simplex, but 4 simplex. Because this thing is the 4 simplex. Okay, and of course, this is just the one of the rows of Pascal's triangle, because those rows describe the combinations. Okay, so the n-dimensional simplex is formed by joining one vertex to the n-1 dimensional simplex. The n-1 dimensional simplex has n choose k plus 1 elements of dimension k and nk elements of dimension k minus 1. So joining each new vertex to each of the latter produces nk new elements of dimension k. Okay, that illustrates Pascal's identity. So, this is the identity basically that forms Pascal's triangle. Right, so let me show you what this means then. Okay, so like Pascal's triangle. We have 1, 1, 1, 1, 2, 1, where for each term is the sum of the two terms diagonally above it. 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, and so on. So for example, let's take these two rows, 1, 3, 3, 1, 1, 4, 6, 4, 1. And these don't really have geometric meaning for us, so just ignore those for now. Okay, this row represents the triangle. This row represents the tetrahedron. Okay, the triangle has 3 vertices, 3 edges, 1 triangle. The tetrahedron has 4 vertices, 6 edges, 4 faces, 1 tetrahedron. So I can form the tetrahedron by taking a triangle in the plane and putting a vertex up above it and joining that vertex to each of the 3 vertices of the triangle below. So for instance, think about the 6, the number of edges of the tetrahedron. Okay, where do those edges come from? Well, there are 3 of them are edges in the triangle. So that's this 3. So this is edges in the triangle. And 3 of the edges in the tetrahedron come from vertices in the triangle, because each vertex, when I link it up to the new vertex, gives me a new edge. And I labeled those backwards. Sorry. Okay, this 3 is vertices in the triangle. This 3 is edges in the triangle. And when I add those up, I get the number of edges in the tetrahedron. Or again, let's look at this 4. Okay, this 4 represents the number of faces in the tetrahedron. Okay, each so where do those faces come from? One face comes from the face in the triangle. That's this 1. This is the 1 triangle, which forms one of these triangular faces. The other 3 come from the edges in the triangle, because for each edge in the triangle down below, I'm going to get a triangular face of the tetrahedron. So we have 3 triangles up in space, and then the 1 triangle down in the plane. And the same is true for each of these. Yes, so for example, if I take the next pair of rows, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. You know, I pick any of these elements here, like this 10 right here. This is the number of edges in the 4 simplex. Okay, this 4 is the vertices in the tetrahedron. Okay, and joining each of those 4 vertices to this new vertex up in hyperspace forms 4 of these edges. But then I also have the 6 edges in the tetrahedron. And those get adopted by the 4 simplex. So you've got the 4 edges up through hyperspace that come out of these 4 vertices in the tetrahedron in space. And then you've got the 6 edges that we already had. And together that gives you all the edges in the 4 simplex. And so in general, like the number of k-1 dimensional objects plus the number of k-dimensional objects in the n-1 dimensional simplex, when you add those 2 numbers together, you're going to get the number of k-dimensional elements in the n-dimensional simplex. So for example, the number of vertices plus the number of edges in the tetrahedron give you the number of edges in the 4 simplex. The number of edges plus the number of triangles in the tetrahedron gives you the number of triangles in the 4 simplex, and so on and so forth. And so this is kind of a geometrical way of illustrating that Pascal's identity, which is how the Pascal's triangle works. Each of these elements can be found by adding the 2 elements diagonally above it. Okay, so you can also define the general n-dimensional simplex as a finite region of n space enclosed by n+1 hyperplanes, or n-1 spaces. So a hyperplane is a space that is 1-dimensional below the space you're talking about. For example, if you're talking about the 2-dimensional plane, the quote-unquote hyperplanes would be lines. If you're talking about 3-dimensional space, the hyperplanes would be ordinary planes. If you're talking about 4-dimensional space, the hyperplanes are 3-dimensional subspaces. So for example, using this idea, the 2-dimensional simplex, that's a triangle that can be formed by 3 lines. Or again, the 3-dimensional simplex, that can be formed by 4 planes. The 4-dimensional simplex can be formed by 5 hyperplanes, 5 3-dimensional subspaces of 4-dimensional space. Okay, now if all of the edges are equal, then you get the regular simplex, which we're going to denote by alpha n. So alpha naught is the point, alpha 1 is the line segment, alpha 2 is an equilateral triangle, alpha 3 is a regular tetrahedron. And then what I have drawn here are orthogonal projections of a rotating copy of alpha 3 into 2 dimensions. So I think maybe it'd be worth constructing this. It's just 2- and 3-dimensional stuff, but it'll help us with the analogy in a moment. But notice how this one 3-dimensional object has all these different representations in 2-dimensional space. Okay, but let's try to do this in GeoGebra. Okay, so I'm going to do something that may not seem intuitive at first. It may seem like I'm overcomplicating it, but it'll help us when we are trying to do this in 4 dimensions. So let me begin by just making a tetrahedron in space. And this is just to illustrate. It's not going to be what I use to actually graph in a moment. But an easy way to form a tetrahedron in space is to just take the alternating vertices of a cube. Okay, so I'd have 1, 1, 1, -1, -1, 1, 1, -1, -1, -1, 1, -1. Okay, so there's the vertices of our tetrahedron. Okay, but I want to be able to rotate that tetrahedron in kind of a careful way. There's 3 ways I could rotate something in space, basically. I can rotate around the x-axis, I can rotate around that y-axis, and I can rotate around the z-axis. So let's make sliders for those. Okay, so I'm going to make it an angle. Let it go from 0. I want to do it 0 to 359 because I don't want any repeats. Increment of 1 degree. And I don't want to call it alpha because it'll be a pain to type that every time. Let me just call it, I'm going to call it A. And I redefine the pyramid, that's fine. So we'll also make an angle B. Same thing. 0 to 359, increment 1. Angle C, same thing. Okay, so we've got these three angles. Now I'm going to make three matrices. These are going to be rotation matrices. To make a matrix, you just make a list of lists. And the first matrix, I want it to represent rotation around the x-axis. So it's going to look like this. So I do, brace, brace, because I'm making a list of lists. The first row in the matrix is going to be 1, 0, 0. The second is going to be 0, cosine of A, sine of A. The third is going to be 0 minus sine of A, cosine of A. Okay, so that's a rotation matrix. So I remember what it is. Let me call it capital X, because it represents rotation around the x-axis. So if I were to multiply a point or something by that, I could actually multiply the point A, I think, x times A. Let me bring the axes back. So I multiplied the point A by that matrix. You can see as I change that angle, that point revolves around the x-axis. Okay, so that's rotation around the x-axis. And, I could do the same thing to all of those points. But let me delete that. I was just using that to illustrate. Okay, now I'm going to make a matrix for rotation around the y-axis, and I'll call it capital Y. So this will be cosine B, comma 0, comma sine B, zero, 1, 0, minus sine B, 0, cosine B. Okay, so that represents rotation around the y-axis. And then we'll do rotation around the z-axis using the angle C. So z is cosine of C, sine of C, 0, comma, minus sine of C, cosine of C, 0, 0, 0, 1. And so that represents rotation around the z-axis. So if I multiply those three matrices, then I get this single matrix, which I call M. And M represents simultaneous rotation through these three angles. We've rotated by A around the x-axis, through B around the y-axis, through C around the z-axis. And if I want to rotate my tetrahedron, let me just hide everything. I'm going to rotate each of those points. I'm going to end up deleting them in a moment, but let me just show you what the idea is here. So M times A, M times B, M times C, M times D. Can I get these four? I don't know what that is. these 4 points. And let me create the tetrahedron for them. Okay, so now if I move my angles around, it rotates my tetrahedron in space. So let me go back to the original position. So that's the initial position. Okay, but if I want to adjust that, I just change the angle. So here I'm rotating around the x-axis. Here I'm rotating around the y-axis. And here I'm rotating around the z-axis. And then, I can combine all 3 to rotate to any position I like in space. So, are there any questions how I'm doing that?
The only question I had, Dr. Teese, was how you got those matrices in the first place, but I understand the rotation aspect of it.
Like, just how did I know to define them that way?
Yeah, that your X, Y, Z.
Well, I mean, you can just take it on faith in this class. However, I know it's been a while, but we talked about them in that Lie groups class. Like, these would be elements of what we called SO3 in that class.
Okay.
So we're talking about like rigid rotations of 3-dimensional space. So, it's basic trigonometry, really. Like, if you think about, if I multiplied, let's say, the matrix X times a vector XYZ, then it would give me X comma cosine Y plus sine Z comma minus sine Y plus cosine Z, which would represent that rotation through that angle about the x-axis. So, so it's really basic trigonometry if you think about what the matrix does. But yeah, these are the basic types of matrices we see in what we call that special orthogonal group. So it's just linear algebra, basically.
Okay.
Yeah, so we can use them to, rotate this guy around these 3 axes. But what I'm interested in right now, I'm trying to build up to doing this for 4 dimensions. So I want to figure out how could I use the information I have so far to plot something in 2 dimensions. So here's one idea that would occur to me. I'm going to make a matrix. We'll call it V for vertices. And in this matrix, I want the columns to be the points, the 4 points, the 4 vertices. So maybe I should write it out first. Right, so we have the points 1, 1, 1, -1, -1, 1, 1, -1, -1, and -1, 1, -1. Let me double check that that's the order I had. Yeah, that looks good. So I'm going to make this matrix whose columns are going to be these points. And my idea is going to be that I could multiply my rotation matrix times V, and I get some new matrix. But the columns of that new matrix would be the rotated points of my tetrahedron. So let me just copy down this matrix. One, negative one, 1, negative 1, 1, negative 1, negative 1, 1. One, negative 1, negative 1. Okay, so I'll call V prime M times V. Okay, this matrix represents the 4 rotated vertices. So look at, like, compare it, let's say, with E, this point E. See that the coordinates of E are the components of this first column. The components of F are the components of the second column, and so forth. So the 4 columns here are these 4 points. Okay, and the reason I'm doing this is because GeoGebra does not, obviously it doesn't graph 4-dimensional things. So I don't have the ability to make a 4-dimensional point, X, Y, Z, W, or whatever, and then multiply a matrix by that. I can't do that. But what I can do is make a matrix and then multiply the matrix by whatever my rotation matrix is. And that gives me a new matrix with the rotated vertices. So now I'm going to use that matrix, V prime, to get the 2-dimensional points. So let's see here. Well, I'll just do them one at a time by hand, probably. Probably, ultimately, it'll be the easiest thing to do. So we'll just make a point. It'll be element V prime, comma 1, comma 1. That's the 1, 1 component of V prime, comma element V prime. Okay, second row, first column. And so what this is doing is it's taking this point E and it's projecting down into 2 dimensions. So you see, if I take this point right here and I just project it straight down into the XY plane, I get this point. That's this point right here. And I do the same thing for the other 4 columns. So I just change that second number in each case. Okay, 3, 3. And so I get these 4 points in the XY plane, and it's the projections of these coordinates of the points, the vertices of my tetrahedron into the XY plane. And so, I can move my shape around, and those points move around in the XY plane. Okay, so I can complete my picture in the XY plane now. By connecting each vertex to all the other vertices. As I look at it moving around in the XY plane, it does look like a three-dimensional picture moving around. But it's defined as just four vertices and 6 line segments in the XY plane, which you can see if you look at the picture in 3 dimensions. Okay, but part of the point of doing this is that this picture in the XY plane did not require the definitions of the 4 points in space. Those are there to illustrate, but I didn't need them. I just needed this V prime matrix. So are there any questions about how I've created this? Okay, so now we're gonna go up a dimension. Now that we understand this. Okay, but now when we're talking about the 4th dimension, we're going to be kind of stumbling in the dark. We can't graph it, but we can graph the 3-dimensional projection. So we're going to be projecting the 4-dimensional thing into 3 dimensions now. So we're going to start over. And we'll begin by defining the matrix for the vertices. And we need a set of vertices for the 4 simplex. Let me see if I can find them in here. I'll have to look them up otherwise, or find them somewhere else in my notes. Let me just look at my old file. Okay, 2, 2, 2, 2. So let me just write these down for a moment. Okay, so the vertices of the 4 simplex in 4-dimensional space can be written as follows. We have 2, 0, 0, 0, 0, 2, 0, 0, 0, 0, 2, 0. Make sure I'm doing that right. 0, 0, 0, 2. And the 5th point is tau, 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 tau. Or remember, tau is 1 plus root 5 over 2. So our vertex matrix is going to be the first column 2, 0, 0, 0, and then 0, 2, 0, 0, 0, 0, 2, 0, 0, 0, 0, 2, tau, 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 tau. Okay, so this will represent the 5 vertices of the 4 simplex. And you can use the Pythagorean formula to check that these are all equidistant from each other. Okay, so I'll make this, but then in 4 dimensions, there's a lot more ways you can rotate. Instead of rotating around lines in the 4th dimension, you rotate around planes, which is not something we're accustomed to thinking about, but that's how it works. So instead of rotating around a single axis, you rotate around a whole plane. So, and there are 6 different coordinate planes. That's more, using combinations. There's 6 different coordinate planes. So really we need 6 different rotational matrices, which is kind of a pain, but we'll just deal with that. Okay, so let's start over here. So angle A from 0 to 359, increment 1. And we need 6 of these, so we're just going to keep going. Okay, so there's our 6 angles, and I'll just kind of scramble them up so that they're not matched. Okay, and we're going to need 6 rotation matrices. Let's think about a good order. Make sure we don't miss any. So let me write some things down again. So we have, we'll think of our coordinates as x1, x2, x3, and x4. Okay, well, we've got the if we rotate around the x1, x2 plane, the x1, x3 plane, x1, x4 plane, the x2, x3 plane, the x2, x4 plane, and the x3, x4 plane. Okay, so those are all the different planes we can rotate around. So I'll begin with the first one. I'll call this matrix X1, 2 to help me remember what it is. And it'll be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, cosine of A, sine of A, 0, 0, minus sine of A, cosine of A. And whichever plane you're leaving alone, that's where the ones go. Okay, and the other ones you get the cosine, sine, minus sine, cosine. Okay, so we'll just kind of keep going through these. X1, 3, 1, 0, 0, 0, 0, cosine of B, 0, sine of B, 0, 0, 1, 0, 0, sine of B, sorry, minus sine of B, 0, cosine of B. Okay, so it rotates around the X1, X3 plane. So now the X1, X4 plane. 1, 0, 0, 0, 0, cosine of C, sine of C, 0, 0, minus sine of C, cosine of C, 0, 0, 0, 0, 1. Okay, so we're halfway done. X, 2, 3, rotate around the X2, X3 plane. Cosine of D, 0, 0, sine of D, 0, 1, 0, 0, 0, 0, 1, 0. Minus sine of D, 0, 0, cosine of D. Okay, X, 2, 4, rotating around the X2, X4 plane. Cosine of E, 0, sine of E, 0, 0, 1, 0, 0, sine of E, 0, sorry, it's minus sine of E, 0, cosine of E, 0, 0, 0, 0, 1. Okay, one more. X, 3, 4. Cosine of F, sine of F, 0, 0, minus sine of F, cosine of F, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And then if I rotate if I multiply all of this, I'll call this M. M is equal to x12 times x13 times x14 times x23 times x24 times x34. Okay, so I get this kind of super matrix that represents all those rotations at once. Okay, are there any questions so far? All right, well, now I need to make the vertex matrix. Okay, this is the one that I wrote down. So it'll be 2, well, first I need to make the golden ratio. So I'll call it T for simplicity. 1 plus square root of 5 over 2. Okay, then so now let me make the vertex, the vertex matrix. V equals 2, 0, 0, 0, T, 0, 2, 0, 0, T, 0, 0, 2, 0, T, 0, 0, 0, 2, T. Okay, so this represents the vertices. Now I'm going to multiply M times that matrix. We'll call this V prime again. Okay, so this is the set of 5 vertices I get after I rotate these 5 points through space around the planes, the coordinate planes, through the prescribed angles. Yeah, so now I just need to plot the points, just like I did before. But now instead of doing 2-dimensional points, I'm going to do 3-dimensional points. So the first one is going to be the point element of V prime 1, 1, comma element V prime 2, 1, comma element V prime 3, 1. So I'm just removing the fourth coordinate, the x4 coordinate. x1 is x, x2 is y, x3 is z, x4 I'm just going to ignore that, and so I'm just projecting along the x4 axis into xyz space. Okay, so I get that point, and I'm just going to do that for each of the columns of V prime. So I just take that same command I just used and change the 1 to a 2, and then change the 2 to a 3. And so on through all 5 columns. Okay, so there's my 5 points in space. And, you know, if I move my angles around, you know, you can see those shift around among each other. Okay, when I rotate, you know, when I rotate around let me think. When I rotate around certain planes, I'm just going to see a normal rotation in 3 space. I guess it's when I rotate around the x1, x4, x2, x4, and x3, x4 plane. I just see a normal rotation in 3-dimensional space. So maybe in hindsight, I could have eliminated those from consideration, the x1, x4, x2, x4, and x3, x4. So we'll kind of keep that in mind for homework purposes. I guess I hadn't thought of that before, but we won't worry about it right now. So the 5 simplex, or the 4 simplex, has a triangle for each 3 vertices I take. So I'm just going to make all of the triangles. And there's 10 of them, so I can use that to kind of count. Up to 5. I'm going to make these opaque, because otherwise it's kind of hard to tell what I've done. Okay, so I need one here. We're up to 7. And make those opaque. Okay, so now I'm going to shift my angles around so I can see better. Well, here's another one that I haven't done. Okay, probably be more systematic than I'm being, but it's okay. Oops. Okay, here's the last one. Okay, so let me modify a bit so we can see everything clearly. Okay, so as I move these angles around, it seems to kind of change shape. But the actual simplex up in the fourth dimension is not changing shapes. Let's do those. There we go. You know, it's just rotating around, and then it's our projection in three-dimensional space that's changing shapes. So, you know, if I orient this various ways, it looks like what we've been drawing on paper. But, you know, we can also orient it to look like that initial picture we drew of the pentatope. Let's see if I can get it just like that. Okay, but so anyway, you know, here's the three-dimensional projection of this four-dimensional force simplex. So are there any questions about how we were able to do that? Okay, well, let's proceed. So here's some pictures of the kind of thing we just constructed. Okay, so let's talk about some other polytopes. So you know, what we were just talking about is extending the triangle tetrahedron pattern into 4 dimensions. Now we're going to extend the octahedron pattern into 4 dimensions. So these are called cross polytopes. So you begin with the idea is basically to start with what's called a Cartesian frame, which is a set of mutually perpendicular line segments, all meeting at their midpoints. So in the XY plane, you have this red frame formed by 1, 0, 0, 1, negative 1, 0, 0, negative 1. Okay, so if you connect the vertices, those 4 vertices, you get a square. Okay, so the actual cross, the actual Cartesian frame is not part of the final picture. Use the Cartesian frame to get the vertices. Okay, so you can do the same thing to get the octahedron. Okay, that's formed from a Cartesian frame in 3 dimensions, where you have 1, 0, 0, 0, 1, 0, and so on and so forth. And if you take those 6 points on the X, Y, and Z axes and join them, you get the octahedron. Okay, so if you continue that analogy into the 4th dimension, you're going to end up with 8 points. Okay, each pair is going to be on one of the coordinate axes, x1, x2, x3, or x4. And if you join all of those points, you each point to the adjacent points, then you get what's called the cross polytope beta 4. Okay, and you can think about these all as dipyramids also. So, you know, if you start with a square, you can think of the octahedron as a dipyramid on a square. But then if you start with an octahedron and form a 4-dimensional dipyramid on the octahedron, that forms the cross polytope beta 4. And so I've got some pictures here. This first row represents beta 3, the octahedron, represented projected into 2 dimensions. And then this, these represent beta 4 projected into 3 dimensions. So let's try modifying our construction. And I think we can do it without too much disruption. So let me go ahead and save as rotating cross polytope. And I'm just going to delete the V matrix. But we'll keep the rotation matrices because those are still good. And in fact, let me get rid of some of these. I'm going to get rid of anything involving x4, because if I rotate around the plane x1, x4, and then project, that amounts to just rotating around the axis x1. But I can handle that just as well by rotating the picture. So I'm going to get rid of x14, x24, and x34. The angles F, E, and C, just for simplicity. And now I'll make the matrix M equals x12 times x13 times x23. Okay, well, so I'm going to make, I need to make my vertex matrix. Let me write those down first. So we've got, the cross polytope. We have 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, negative 1, 0, 0, 0, 0, negative 1, 0, 0, 0, 0, negative 1, 0, 0, 0, 0, negative 1. And so it's going to be helpful, I think, to kind of think about how these are all going to be connected when I actually draw this thing. Let me make a little ring of points. And then we'll make it in an octagon since there's 8 points. Okay, so we'll start with, I'll just put 1, 0, 0, 0 right here. 0, 1, 0, 0. 0, 0, 1, 0. 0, 0, 0, 1. And then diametrically opposite each of these, I'll put the negative of that. So opposite this point, we're going to have negative 1, 0, 0, 0. And then here we have 0, negative 1, 0, 0. This point is going to be 0, 0, negative 1, 0. Then 0, 0, 0, negative 1. Okay, and each vertex is connected to all the other vertices except the one that's opposite it. Just like in an octahedron, each vertex is connected to the other vertices except for the one that's exactly opposite. Like, that when we have the coordinate axes like this, I consider this point, for instance, that's connected to this point, this point, this point, and this point, but not to this point. So like this 1, 0, 0, 0. Is connected to these 6 points, but not the one that's opposite it. Oops, and I just drew the one that I wasn't supposed to. Okay, so I'll put a dashed line there to remind us that we don't connect those, but we connect it to these other 6. And same for the other ones. So I drew this to kind of help us figure out which segments we're actually going to want to draw in a bit, because that can be tricky. Okay, but so at any rate, here's the vertex matrix. We have 1, 0, 0, 0. Whatever. 0, 1, 0, 0. 0, 0, 1, 0. 0, 0, 0, 1. Negative 1, 0, 0, 0. 0, negative 1, 0, 0. 0, 0, negative 1, 0. 0, 0, 0, negative 1. Okay, so that'll be our matrix V. Okay, so I'll go ahead and enter that in GeoGebra now. So 1, 0, 0, 0, negative 1, 0, 0, 0. Next row, 0, 1, 0, 0, 0, negative 1, 0, 0. Third row, 0, 0, 1, 0, 0, 0, negative 1, 0. Fourth row, 0, 0, 0, 1, 0, 0, 0, negative 1. And then I just do M times V. This will be V prime. And now I'll do the points that I get by projecting. So it's just element v prime 1, 1, element v prime 2, 1, element v prime 3, 1. And replace the 1 with 2. And so on. So I'm doing them by hand. It might be easier to do these as a sequence. Let me think about that. I think what I'll do is this. I'm going to make a sequence instead of doing each of these by hand. But, you know, if you put a point on a sequence, it's kind of unstable. So I'm going to have to be careful about that. So I'll do sequence of things like this. So I'll do comma K for this, where K goes from 1 to 8. Let me try redefining that. Okay, so there's the vertices. But now I need to try to do the segments. And I think the best thing to do would be create the 8 points, which is a little easier to type out now that I have the list. So I'll just do, you know, element L1, comma 1, and see that creates a point there. And then I'll just do that for each of those. Just so I have the points individually, not as a list. Okay, so let me put everything back in the original position. Just to help me connect everything. Okay, so I'm going to draw segments now. And I'm going to use the menu to do it instead of the points, because I think the menu will make it easier. I just want to make sure to connect each point to all of the points except the opposite. And if I just start with A and work my way down, and then B and just go down from B and so on, then I won't be repeating everything. So A gets connected to B, A gets connected to C, and to D, not to E, gets connected to F, to G, and to H. Okay, B gets connected to C, B gets connected to D, E, skip F, G, and H. C gets connected to D, to E to F, skip G, connected to H. Okay, D connects to E, F, and G, but not to H. Okay, E gets connected to F, G, and H. F gets connected to G and H. G gets connected to H. So I hope that's everything. Let me move things around and see if it looks good. I think it does. Okay, so there's the edges of my cross polytope. I haven't done the faces yet, so that remains to be done. Maybe I'll stop there though. You know, each of the triangles that you see formed by three edges is a face. So it's just a matter of making all of those faces. And it can be easy to get lost in here, so you should try to be as systematic as you can. So are there any questions so far about how I was able to do that? Okay, so again, we're just taking the points that are 1 unit away from the origin on each of the 4 coordinate axes in R4, rotating and then projecting. And then that gives us this nice picture that we can rotate around to get different views of it. Okay, so beta n, the cross polytope beta n, is a dipyramid on beta n minus 1. In each of the alpha k's, each of the simplices in beta n is either an alpha k of beta n minus 1, so it's an alpha k of the thing that we built on, or it's one of the 2 pyramids on an alpha k minus 1. So the number of alpha k's, the number of the k simplices in beta n is the number of k simplices in beta n minus 1 plus twice the number of k minus 1 simplices in beta minus 1. And it's twice because there's one for each of the 2 pyramids, the pyramid on top and the pyramid on bottom, so to speak. So you can use mathematical induction to show that the number of k elements in beta n is 2 to the k plus 1 times n choose k plus 1. So if you use this formula on beta 4, that's our cross polytope beta 4. Has 8 vertices, 24 edges, 32 faces, 16 cells. Yeah, so I think it's worth thinking about that for the octahedron, because that's the example that we're familiar with. So think about what this statement would say for the octahedron. Yeah, we think of forming the octahedron from the square. So you've got the square in the plane. and then you put a dipyramid on it. So you put a point on top and a point on the bottom. Okay, so let's think about what our statement would say about this. So we're getting the beta 3 as a dipyramid on beta 2, which is the square. Okay, so each alpha K and Bn in beta 3 is either an alpha K in the beta 2 or the pyramid on the alpha K minus 1 in beta 2. So for instance, if I think about line segments, okay, each line segment in this beta 3 is either a line segment in beta 2, so like one of these 4 segments, or it's a quote unquote pyramid on an alpha 1 in beta 2. On an alpha 0 in beta 2. And alpha 0 would be a vertex. And the pyramid, the quote unquote pyramid on that would be this line segment or this line segment. Okay, or again, each alpha 2 in the octahedron is either an alpha 2 in the beta 2, the square, but the square doesn't have any triangles, so there are none of those. Or a pyramid on an alpha 1 and beta 2. So that would be a pyramid, quote unquote, on one of these 4 segments. And the pyramid would be the triangle. You're taking this point above the plane and then forming the triangle. That's the quote unquote pyramid over that segment. And for each segment, there's 2 pyramids like that. And so in this case, well, yeah, so the number of alpha K's is going to be the number of alpha K's in beta 2 plus 2 times the number of alpha K minus 1s in beta 2, because there's 2 pyramids for each of these alpha K minus 1s. So for instance, the number of edges is the number of edges in beta 2 plus 2 times the number of vertices in beta 2. Because for each vertex in beta 2, you have this edge and this edge. Okay, so then using that formula together with mathematical induction, using the fact that the number of vertices is 2 times n, because we're forming this from the Cartesian frame. Mathematical induction proves this general formula. So for example, let's do it for beta 3 just to make sure we understand it. N1, the number of edges. That's 2 to the k plus 1, so it's 2 squared, times n choose 2. N is 3. 3 choose 2. So it's 4 times 3 times 2 over 2 times 1, which is 12. So there's 12 edges, which is what we got. And n2, the number of triangular faces, is 2 cubed times 3 choose 3, which is 8 times 3 times 2 times 1 over 3 times 2 times 1, which is 8. There's 8 faces. Okay, so the third major type of polytope to talk about right now is, well, we'll see it's the hypercube. So, and this is the one that's talked about in flatland. So when you move the point pi naught along the line, you trace out a pi 1. When you move pi 1 in an independent direction, trace out a parallelogram. When you take the parallelogram and you trace it, you move it in the parallel direction, sorry, in an independent direction, then you get a parallelepiped, and so forth. So the n-dimensional version of that is called a parallelotope. Okay, so for instance, you know, when at the beginning of today, when we move the point to get the line segment, move the segment to get the square, move the square to get the cube, and then the idea would be you move the cube in a fourth direction to get this 4-dimensional version of a cube. So the n-dimensional parallelotope has 2 to the n vertices. Again, this came from that flatland quotation. This is the geometric sequence, the number of vertices. A cube has 8 vertices. The next dimension up would have 16 vertices. And its other elements are parallelotopes. So like in a parallelepiped, the faces are parallelograms, the edges are line segments, the vertices are points. If I had a 4-dimensional parallelotope, the cells would be parallelepipeds, the faces would be parallelograms, and so forth. And you can think of an n-dimensional parallelotope as formed by joining 2 parallel n-1 dimensional parallelotopes with lateral parallelotopes. So it's kind of like, you know, if you take, well, it's just forming a slant prism basically. You take a parallelotope and then a parallel parallelotope, and you join the vertices to vertices with edges, and then you complete the faces and so forth. That produces the parallelotope. So each k-dimensional parallelotope in that picture either belongs to one of the 2 bases, or it's formed by adjoining a pair of k-1 dimensional parallelotopes in the bases. So the number of k-dimensional elements in the parallelotope is the number of k-dimensional, 2 times the number of the elements in each of the bases, plus the number of k-1 dimensional elements in the base. And so the number of k-dimensional elements in the parallelotope is 2 to the n-k times n choose k. So this is very similar to the cross polytope explanation. I'll just let you think about it. I'd rather get on to trying to visualize these. But here's a picture. If I look at this parallelepiped here on the right, each element in it is either going to be an element in the base on the top or the base on the bottom, or something connecting the two bases. So, for each segment in the base, you have a parallelogram on that segment. But then you also have the parallelograms of the bases. Okay, then each edge is either an edge in one of the two bases, or it's an edge that's connecting the corresponding vertices. So again, the number of edges is going to be twice the number of edges in the base plus the number of vertices in the base, because each vertex in the base gives you one of the edges. That's where this formula is coming from. Okay, and if you just take n linearly independent vectors, then adding them up in various ways forms the parallelotype. So like this parallelotype, if I take these three vectors and I just form all the possible sums of them, then that gives me the vertices of this parallelepiped. It's what we did when we formed zonahedra earlier in the semester. But you could do 4 linearly independent vectors in 4-dimensional space, or 5 in 5-dimensional space, and so on. And doing the same kind of thing gets you that n-dimensional parallelotype. So if I take all the integer sums of these vectors, that forms a lattice in space, or whatever, n-dimensional space. Okay, they're the vertices of an n-dimensional honeycomb whose cells are equal parallelotopes. So just like you can fill the plane up with parallelograms by adding the vectors, or you can fill space up with parallelepipeds, the idea would be you fill up higher dimensional space with parallelotopes. And if the n vectors are mutually perpendicular, the parallelotope is called an orthotope. If the vectors also have equal length, so they're all perpendicular, they're all equal, then the parallelotope is a hypercube, which we call gamma n. So gamma 1 is the line segment, gamma 2 is the square, gamma 3 is the cube. Gamma 4 is the thing that the square was trying to get at in flatland. Okay, that would be gamma 4. And that's, I have a schematic diagram of that here on the right. So you can think of this as taking like 2 cubes like this and joining the vertices. Okay, or you could, instead of just doing the hypercube, you could form the cubic honeycomb, the lattice. So if I take a square and I form the lattice from that, that forms the square tiling. If I take the cube and I fill space with that, that forms the cubic honeycomb, which we referred to as 4, 4. If I take the cube and fill space, if I take the hypercube and fill 4-dimensional space with that, that forms a higher dimensional cubic honeycomb. Okay, and the hypercube is also called the measure polytope because you can use it as the basis of measure in n-dimensional space. So here are some pictures of a copy of the hypercube rotating in three-dimensional space. Let me think. So I probably don't have time to go into the details of that, but let me just say, you know, I can do it easily now with my setup by just creating a new set of vectors. We're going to have 16 vertices now, so it's a larger matrix, but you know, I just multiply it by m like I did before, and so on, and I get this rotating hypercube. Let me try to open up my file instead of making it from scratch. Yep, that's the wrong one. Well, here's the cross polytope, incidentally, with the faces completed. Okay, but what I want is what's called the 8 cell. Okay, and you know, you can think of it as just two cubes that are parallel to each other, and you've connected the corresponding vertices. But yeah, so this is a parallelotype in which the cells are not tetrahedra as they were in the previous examples. They're cubes. So this is made up out of cubes. And if I take any single edge, it's the edge for three different cubes. Like if I take that edge right there, let me color it different. So that this one that I've just colored red. Make it thicker. Okay, that edge, it's the edge for three cubes. You know, there's this one that's kind of the obvious one that's kind of sticking out at us. So here's, you know, a face of that cube. It goes back here like that. So this cube that I'm tracing out right now, that's one of the three cubes that share that red edge. There's another one, this one that's kind of squashed on top. So let me trace that out now. So you see these. Parallelograms are all part of that cube. And then you've got a third one that's kind of squashed in front. So you have this one that looks like this. So that, you know, they don't look like they're cubes because we've flattened them into three-dimensional space, but in four-dimensional space they're cubes. And there's three of them meeting at that edge, and each edge is shared by three cubes. Okay, well, so are there any questions or anything? Okay, well, I guess we can call it a night there. So I'm recording this meeting, and it takes a while for these recordings to process, and this is going to be a long recording since it's a 3-hour class. So it may take me a while to get it posted if it works at all. But I'm going to try to post it. What I've been doing for all my classes is just I post it on YouTube because it's easy to watch there, and then I link it in Blackboard. So I'll try to do that. I also have the slides on Blackboard, so it's really we're better off than when we were meeting in a regular classroom. That's not true of my other classes, but it kind of works out for this one, I think. So, I'll be posting some homeworks either tomorrow or Friday, and it'll be due next Friday. And it'll involve constructing some of the stuff we did today. So, any questions about anything? Okay, well, I guess we'll call the night there. So you all have a good week, and I'll see you next week.
Dr. Ortiz. Thank you.
All right. Yeah, take care.